Wow, what's going on here? Well, I'll tell you, what I did was I picked up that word modelling up the top here and I Google searched it, okay? And this is what I came up with. I think I should have added with trig functions. I think it's a different type of modelling than this lot here. Anyway, quite good looking faces there. Let's go down and let's look at modelling with trig functions. And I think this couple of diagrams and a formula says it all. If we, for example, had a plot of data that looked like this, and we saw that there was like a sine curve happening there, maybe we could work out a formula for it and then draw a graph. So that's the idea of mathematical modelling. And we're going to have a look at some examples now, and it's quite an exciting area and useful area of mathematics. So let's have a look. What is modelling? Well, it's not just on the catwalk, mate. In mathematical terms, here's the Huddy definition at least. It's a mathematical description of a practical situation, using perhaps a graph or a formula to have a better look at what's going on there. Okay, so that's the definition of the modelling that we're going to be doing now. And here's my burning hot red hot question for you here. When might we use trig functions in modelling? When do you think, in a practical sense, and we'll start off with positive x values, I think, in the real world, when do you think you might get this cyclic behaviour going on and on? Something which is periodic, has a regular repeating interval or period from the graph work in earlier presentations. What sorts of things could x and y be? Can you think? You might pause the presentation and think about things that perhaps go like that. If you're looking carefully up above, when we're up there at that graph, you would have seen an example. What is that? Oh, it's temperature, isn't it? Temperature throughout the course of a year and ongoing, because it's seasonal. And so you're going to have a periodic function responding to the seasons. Is there anything else you can think of? What about tides coming in and out due to the gravitational effects of maybe the moon in addition to the sun? Is there anything else? Something in physics perhaps? What about alternating current? AC current. Alternating, changes direction backwards and forwards, and so many cycles per second. Okay, 240 volt AC, 220 in America, in the States. So, cycling backwards and forwards, and so alternating current. So all of these can be represented by a graph which looks like that. So what we're going to do here is to have a look at a couple of practical situations which can be modelled with our knowledge of sine and cosine functions. Let's go and have a look. And the first one is, of course, the one I had up earlier, and that is we've taken some monthly maximum temperatures, and the mean monthly maximum temperature. Okay, so we're plotting those for each of the months. Here is the mean maximum temperature in degrees Celsius. Okay, so we could plot that. Here it is here. Notice that we would normally use a number here. Month 1, 2, 3, etc. If we're going to use a mathematical model there, we'll have numbers for the months. And now we've plotted it. It certainly looks like a sine curve. Or could it be a cosine curve? Does it matter which one we would use to actually model this behaviour here? Doesn't matter whether it's sine or cosine. Okay, you might think about that, and I'm going to answer that for you a bit later on, because what we need to do is to choose the sort of function that we want there and make sure it's going to be suitable. So let's have a look at going down now and the work involved in trying to model this. So first thing is, I've chosen to model it with a sine function. Okay, now that question's still alive. Why might we stick to sine and not use cos, or would we use combination? I want you to think about that. Anyway, we're going to use this basic model. I'm taking screen clippings here from Hayes and Harris publications. And we know from our work with graphs, this is the amplitude, this is the scale factor, or 1 on the scale factor for a dilation or a stretch in the x direction. This is really a stretch or a dilation in the y direction. That's keeping those two together. This is an x translation by plus c, and this is the y translation, isn't it? Going up in the y direction, creating a new principal or axis there, major axis, or mean position for the sine curve, any of those. So do you remember that? And now here's a very important step here. We can't stay in y-land if we're going to be modelling. We've got to put in the actual variables that we are measuring here. So T takes the place of y, it's the temperature in degrees Celsius, and little t takes the place of x, it's time. Okay, so this is important to get into the context of the question, because modelling is a mathematical description of a practical situation. So the variables, not just x and y, which we usually use conventionally, have to relate to the actual practical aspect. So we're going to try and fit one of these to that data on temperature. So let's have a look down here, and let's do the first, maybe, I don't know whether this is the easiest one, I don't think this is the easiest one, but we'll do this one first. It's finding the b value. Okay, and remember, the b value is the stretch in the x direction. So what we're going to do is use the period of the function to detect that. So here I've started to draw a line in here. The period of the function, when it comes back up to the maximum temperature, assuming that's going to be the maximum there and there, the period of this function is 12 months. Okay, so in our formula where we've got t equals a sine b, t takes c plus d, what we're saying, if we stretch it and in the x direction by a scale factor of actually 1 on b, what will the number of cycles be in 2 pi? If we've stretched it, it'll be 2 pi over b, where b is the number of cycles in 2 pi, because we have stretched it in the x direction. So how long would it be for one cycle? 2 pi divided by b. And we know that one cycle from the graph is 12 months in duration. That's the period. So let's rearrange this now. They haven't shown this here, but 2 pi on b equals 12. Multiply both sides by b. 2 pi equals 12b. Divide by 12, and b is pi on 6. Okay. Using the properties of sine, that the basic function has a period of 2 pi, and if we have more cycles in 2 pi, then the period is going to be reduced by dividing by b cycles. Each cycle will be 1/5 of 2 pi, if you like. Okay, so we've got that value. You should be getting excited now. We're going to actually detect, for this graph up here, what its actual formula is. And we're not going to use technology right up, we're going to use mathematics, and that's more exciting. Anyone can push the buttons, mate. Okay, let's come down here and have a look at the next thing we want to do. The next thing we want to do is work out the amplitude, all right, or the stretch in the y direction. So we've got to tick on that one, and now what we're going to do is try to find the amplitude. Well, this is the maximum deviation from the mean position, or from the principal axis, isn't it? So let's have a look. Somewhere in here is an axis, and we want that distance there. We haven't found the axis yet, so why don't we find the total distance between max and min and divide it by 2. Now what's the distance between the max and the min? Max minus min, so that's 28 degrees minus 15 divided by 2. So it's about 6.5. Okay, so that's the idea. We're going to get the top value, the max, minus the min, find that distance between them, divide by 2. Hey, we're going well here. in detecting the model or the formula for this particular set of data. Let's go down. What's the next one you want to find? I reckon we might find D. D, of course, is what is D? D is the Y translation of the function. Okay. So we've got this one. We've got this one. I'll put an X in there. I'll put a T. And now we want to find D. D is the new position of the principal axis. The principal axis usually for sine is just the x-axis, isn't it? We go up and down on the x-axis. So this has been moved up to somewhere up here. Where is that new line? Well, we could say it's midway, it's always midway between the max and the min. Right, somewhere in the middle there. Where is the middle of two numbers? The middle of two numbers is their mean or their average. Max plus min divided by 2. So it's 21.5. If this is our actual max and min on a regular basis, which we're taking as granted here, for granted in this particular work. So we've found D now. The model's going well. We've only got C left to do. So I'm doing these in little pieces for you. We're up to here. We've got all of these. Okay, and now we want to find C. Well, C is actually here. C is the X translation in the positive direction because it's X takes C. So it's the move to the right. C move to the right from the usual sign position. Right, so you need to know your graphs pretty well from the earlier work. Okay, let's go down and have a look and see if we can detect it. I'll put it all on the screen here now. Okay, so here's our graph. What we need to do is to say that what is the C value? Well, how far is the sign being moved? Well, hang on, what's sine usually look like? Sine usually starts somewhere, here, like this, and goes like that. Well, hang on, that position is usually intersecting with the principal axis, and at naught, at the value naught here, it's sitting on the principal axis. Well, hang on, it's a while before it does that. It's way up here at A. A is where the usual sine graph starts. So that's been moved way up there in the positive direction. How far has it been moved? Well, A should be back at naught, mate. And no, it's not. It's at the 10th month. It's October. So C is 10. We're just checking 21.5 is the axis. So we're trying to say where on the axis should it usually be. Right? It's usually back at naught and on the axis, whatever that is. Here it's 21.5. So we're going to find here the first point where it starts its usual sign behaviour in that upwards curve. Okay, so what's the model? Hey, how exciting was that? We've got the model here. We've got all the numbers, and if we drew the graph over the top of the empirical or measured points, we would have this. This axis should be really numbers, 1, 2, 3, etc. Because when you sub values in for t, you don't sub months, mate. You sub values of that variable. So this is the time, t in months, and they should be numbers along there. Okay, do you get it? Well, that's good mathematical work. What's the calculator say? Let's go back and check it with technology. So here we go, here's technology for you. All right, so bringing this up now, we first of all go to stat mode. Here, this first calculator is stat mode. And in stat mode, we come up with a list. These are the numbers for the months, 1, 2, etc. And these are the temperatures in degrees Celsius. That's your first job. Then you need to choose graph. We're going to draw a graph. So to do that, you're going to hit F1. Okay, and up comes this window. And it gives you the option of setting the graph up. What sort of graph do you want? So you're going to hit F6 to choose that set. Okay, up comes this window. You're going to choose scatter, X list list 1, time, Y list list 2, temperature. Okay. If you exit that, you go back to this other screen back here and hit graph 1, then it draws the graph nicely for you. And yes, it does look like a sine graph still. Okay, now we want to fit a curve, so you want to choose calc, And you do that by hitting F1 in there. And up comes a window, but you need to use the right-hand arrow key to go to the next window, because that's where the sine model is living. You can choose the sine curve to be fitted. Okay, and to do that you'll hit F5. And up comes this window. Oh, it's already fitted a sine curve to it. What's the sine curve? A little bit different from the one we used. It's a sine bx plus c in brackets, so b is not outside the brackets, and it's a plus in here. So this model is considering our data points as being shifted to the left. So that's going to have some different numbers in there. We'll have a look at that model in a minute. Okay, and then if you hit draw, it will draw the model it's got. And then if you come back and hit copy, this is important, this idea of copy, it will copy the function, the model it's created, into the graph mode of the calculator. And if you go to graph mode, you'll see it sitting there. You might say, well, Huddy, why do you want to do that? Well, if you wanted to work out the x and y values of any points on the curve, you might like to use gsolve, graph solve. And you get this in graph mode by hitting Shift F5, don't you? And that allows you to go along the curve, find the max and the min, find the x value for any y value, or the y value for any x value using xcalc, ycalc. So that's a powerful tool, this idea of copying it into graph mode. Well, let's have a look at this formula here. It looks quite different from ours. So come down, and I'm going to write it out now. So this was the model done by hand. That's where we estimated the max and the min to be roughly the measurements that we observed as the means. Now this model is using a different form, okay, a sine bx in brackets plus d, so that's one difference, so it's t equals a sine bt, see the b is in brackets, plus c plus d. So using a different format, so there's two things, the b and the c, but actually more important than that is the way this model is fitted with technology. It's called a least squares regression model, least squares regression. So in actual fact, instead of just taking the maximum to be 28 and the minimum to be 15, it actually fits for all the points a model which will have the regression or the movement of the points, or the squares of the difference of the points from the model minimised. So it's for every point. Come back up here to this calculator screen here. See there that the actual maximum that we recorded is not quite the maximum of the function. The calculator has minimised the differences of all these points away from the model and decided that it really fits, a curve that best fits is one that hasn't got a maximum quite as big as what we said. Okay, so it's a different approach. It is least squares regression, which minimises, makes least, the squares of the deviations or regressions of the data points away from the model. So this was the model, remember? Let's have a look at the model coming off the calculator. T equals. Okay, so come up here. A is up here 6.33 approximately. So we put here approximately, as the book is done, sine, and then bt is 0.519t plus 0.994. Strange figures here, plus 21.5. Those are the figures on this window up here. Okay, well, there's some good things here. Look, 6.33 is almost the same as 6.5. And as I said, the calculator has fitted a smaller maximum here because of least squares regression, getting in the best fit for all points, not just taking the maximum as absolutely that value that we used. And then down the end, 21.5, sorry about that, 21.5 is the same. So we agree with that, the principal axis. All right, what else is to be looked at here? Well, have a look. We have a different format here. As we said before, the b's inside the bracket and there's a plus. So let's change that. Let's divide that b out of the bracket. And if we divide everything by 0.519, which is approximately pi on 6, so that's agreed, or that agrees with the other model, t plus approximately 1.92 plus 21.5. So that's the model with least squares regression from technology. So does this match up? Yeah, pi on 6 is approximately 0.519. Yes, pretty close. But what about this? Okay, what's this saying? This is thinking of our model as a neg 1.92 translation in the x direction, not a plus 10 translation. Well, does that agree? Let's come up here. What did we say? In our model by hand, we said that has started its proper movement 10 to the right. Now, we could think of this as starting the proper movement, the usual sine movement, by what's this? 1.92 to the left. That's what it's saying. Our model is out of kilter. Either we've said we've shifted it back 1.92 or forward plus 10. Let's add those two up. 10 plus 1.92 is 11.92. Because that should be overall a period's width, shouldn't it? Okay, and that is approximately the period, because our period of this function was 12. So allowing for slightly different ways of modelling, we have got slightly different numbers. Do you get the idea though? There's some interesting maths here in relating these two different models. Do you want to think of it as a translation to the right or a translation to the left? And can you see the equivalence of those two models? This is good fun mathematically. Okay, let's go down. You want to do another one? Let's have a look at the other one I mentioned, and that's the tidal models idea. Okay, so here's some information. Tide follows regular patterns or periodic of rising and falling due to the combined gravitational effect from the sun and the moon. So at Outer Harbour on one day it was noticed that there was a high tide occurring at 1:18 and low tides at 6:46 and 7:13. 6:46 a.m. 7:13. High tides the next day in the morning, the afternoon, and low tides morning and afternoon. So we've got, 2, 4, 6, 7 data points. This time we're not going to use technology so much. We're going to try and do it manually again or algebraically. So come down, let's plot it. Plotting the points is always a good idea. So time here, as the statement up here, plotting these times, where t is the time after midnight before the first low tide. Okay, so that first low tide. All right, so here we can plot that, and we can plot some of these others here. And x is going to be a very important point. I wonder whether you can see why. So we can plot some points there, and let's have a look at trying to get a model for this one. You can see we've put in the gaps. In the gaps, we've put the actual spaces we've measured in hours and minutes. Okay. The other thing to know is we haven't put in the actual depth. We're calling a maximum 1, minimum of neg 1, high and low. We haven't bothered actually putting in metres. We've measured that it's fully up the beach at a certain time and furthest down at another time. We're not actually assigning metres to that. Okay, let's have a look now, and going down here, we're going to try and model it with this function. So making it contextual now, in the context, then y will be the height and x will be time. Okay. Now, so the principal axis here, we didn't move it anywhere. D is naught. Okay. So h will be naught there when d is naught. So at 0 time there, that's going to be our situation. Amplitude is 1 because we actually haven't measured the height there. We're going to go with a conventional sine curve from 1 to neg 1. So a is 1. Okay, so it's right on the axis there. D is naught. Okay, so what are we going to do now? We need to find some of the other things. What do we want? We want b, we said we're going to identify it as a sine function, a sine b x takes c plus d. All right, well, let's have a look. What about b? b is the number of cycles. So the period, therefore, is your usual 2 pi divided by how many cycles we get. Okay, and let's have a look at the average period. If we average these numbers between two minimums, that should be a period between these two. They all vary a bit. So let's find the average. And if we do that, we get, add all those up and divide by 3, we get approximately 12.4 hours. So therefore, with b cycles in 2 pi, that should give a period of 2 pi divided by b is 12.5. So b is approximately 2 pi over 12.4, which is 0.507. So we've got our b value. Let's put the formula together a bit. Okay, so here we have the b value. A value is just 1, no d value. So what's c now? How far has it been shifted to the right? Because negative means the transformation work for translations, a plus c shift. Let's try and find it. Well, here's the importance of x that I hinted at before. This is where the usual sign pattern is starting in this particular function, up on that first arch. And it should be back here. It's been moved right up to there. Okay, so that's going to be the c value if we can find that. What is that though? We don't know. We haven't got that in this one. So we can say, we had that one, we measured the first low and the first high, and you know where it cuts the principal axis, or the mean position there, is halfway between a min and a max. So let's go halfway between the two values. This was the time when it was a minimum. This was the next time when it was a maximum on that first day. So if we go halfway between, that's the mean of the numbers. Halfway between is the mean of the two numbers, and that was 10.04. So we've actually got the c value. Let's put it all together now and have our function. So the model is approximately that. Okay, let's now plot that over our points, and we see it's a good fit. So we're not using regression here. We're actually making the function go through the points that we've measured as max and min. And we haven't got other points to minimise the squares of the deviations from, if you like. So it's not least squares regression that we're using with this manual fitting of the model. Okay, here are some problems for you to try. I want you to use the same technique and then to check your answer using a graphics calculator. But I want you also to what? Ensure that the models by hand and with technology are consistent with each other. Now obviously we're using two different fitting methods. A manual one, where we assume the max and min as stated, and one where all the points are up for grabs and technology fits a least squares regression line. So there will be some decimals a bit different, but I want you to see whether it's consistent with the idea of bx plus c in the function versus b outside of x takes c. By looking at that translation up and down the axis there and see if you believe they are consistent. Because the two numbers should do what? Should add up to the period of the function, shouldn't they? Think about that. All right, pause the presentation, have a go at those first two. And if you want to fast forward it, the answers are coming on behind as usual. Okay, I'll go on now. Let's have a look at question 3, 4 and 5. Okay, we'll just go up a little bit here. Up a little bit. Okay. This opening problem, you'd have to look in the textbook to see that. I haven't included that in this presentation. Okay, have a look. There's a lot of words here. Sometimes underline key points and numbers is a good way in problem solving. All right, pause the presentation, have a go. I'm going to show you the answers now. So come down, and here we have the answers. All right, check them out and make sure, check against the technology answers and make sure you can see the relationship between the positives and negatives, between our negative values there, where we're looking at the manual fitting, and the positive as used by the calculator. And the question is still there, isn't it? Would you like to use cosine or would you not bother? What's the answer to that? Using sine or cosine? Does it matter? I'll give you the answer now. Let's have a look. We usually use sine and just stick to that because the two are intimately connected, aren't they? Here's sine and here is cosine. Okay, cosine coming up here to there. So it really doesn't matter because cosine is a translation of sine, isn't it? Cos of theta is the sine of theta translated what? Instead of being peaking there, cos peaks back there. So it's a sine of theta plus pi on 2, if you like. Okay? So cos is actually only a translation of sine. So let's stay with sine and use modelling with that function, because the other one doesn't have anything more to offer. It's just a different translation of sine. Okay, come on and let's have a look now at why model. Why would you do this? Well, we can do this because, or why do we do this? Because it gives us a formula with which we can predict behaviours later. So let's have a look at this one. This time we're given the model already. Somebody's done the work that we just did. Now look at all the things we can do. We can graph the function and we can use it to predict over a time interval the time when the tide was going to be the highest, the lowest, and so on. So first of all, if you're trying to draw a graph, you could do it with technology. Let's just take it this way. Now you know the maximum minimum value of sine is 1. So if you put a 3 in front, it's going to go to 3 down to -3. What other points can we do? Well, first of all, the period is 2 pi over b. If we divide that, invert and multiply, it's 12 hours. So along this axis, we can mark out 12 noon. This is hours after midnight, as it was before. And we can now draw the function. How do you know? Well, if the period is 12, that's the end of the cycle, and you know there are 4 things that happen in a cycle. Starts off at 0, goes to a max, goes to a 0, goes to a min and back again. So you'll divide by 4, and having one of those features every 3 hours. Get the idea? Understanding the graphs of sine and cosine are powerful tools in fitting models. So get the idea. Get the max and the min from the formula. You can then get the period, and then every quarter of a period you go from max to 0 to a min. So you only have to find the first one. So sub t is 0 in here, sine of 0 is 0, and then you're away. Up and down, through 0, down again, and so on. So there are some good little tricks that you can use here if you understand the function. And that's what we're doing in earlier presentations, trying to understand the graphs of trig functions. Okay, when was high tide and what was the maximum height? Okay, so the high tide, if you look at this from 2 points of view, you can look at it from the graph, okay, and find it's 3, and then at 15 hours or 3 a.m., 15 hours is 15 hours after midnight, so that's 3 p.m. The maximum height is 3, and you can see that at points A and B. Or you could sub in to the function. Let's do it that way, a little bit of algebra there. When is this function a max? This is a max. Sine is a max when you're finding the sine of pi on 2. So pi on 6 times t must come to pi on 2. The sine of pi on 2 is 1. So t is pi on 2 divided by pi on 6, which multiplied by 6 on pi, division by a fraction. Oh yes, it checks as being 3. There's a few ways around this. of looking at where that is a maximum or a minimum. And of course there's another one 12 hours later. So there's 3, first one, and then 12 hours later, because the period is 12. And that is the distance between successive maximum, isn't it? Or successive minimum. At 2 p.m, what's this? 2 p.m. is 14 hours after midnight. So stick 14 in place of t in the formula and you get approximate height there, 2.6 metres. Okay, above the mean. Let's have a look then at part D. Part D said, when is the height at least 2 metres so we know the ships can get in? Okay, 2 metres above the mean position. And there's a couple of ways of doing this with technology. We're going to use technology here, not algebra. So we need to solve where the height is 2, that's that one. You could solve this using algebraic means, that's in a later presentation though. What we're going to do is we'll say in graph mode, we'll put that function in and this function in. And then we'll find these points of intersection by, on a Casio, going Shift F5, and that goes to G-solve. And if you've got 2 graphs there, you can find ISCT, intersection. Okay, and it'll give you the times and also to find the values in G-solve. The times, the X values and the Y values. Or you could go to G-solve just with the ordinary graph, not with Y equals 2 drawn, and you could find, do an X calc for a Y of 2 and just go across. Right? X calc, put in Y as 2 and flit across to each of these 4 points up here. And the Casio is a handy calculator. It will give you the X values and the Y values of those points. For any points here, you know the Y value anyway, it's 2. Now, we have to do something in the context of this question. T is 1.39 hours after midnight. Okay, so first of all, 0.39 of an hour is 0.39 times 60 minutes, which is 23 minutes. So it's an hour and 23 minutes after midnight, so it's 1:23 a.m. 4.61 hours after midnight is 4 hours and 0.61 is 37 minutes, so it's 4:37 a.m. 13 hours after midnight, 13.39 is again 1 p.m. in the afternoon and 0.39, 23 minutes. So you must state the final answer in modelling problems in the context of the question. No good saying X's or T's. You've got to come back to what that means in everyday language about what's happening in the problem. So we've got to change to minutes after midnight, and then we have to change to 4:37 p.m. You can't say this was so many minutes after midnight. We don't do that in everyday language. All right, are you ready? I'd like you to have a go now at some problems I've got here for you. Question, I think there's 5 of them. So question 1 and 2, using models now, showing the value of the work that we were doing before. So pause the presentation, have a go, and I'll show you the answers down below. Let's go down to the next problems. 3 and 4, almost 4. We can go a little bit higher, I think. Yep, there's 4. Have a go at using these models. And we'll do the last one now. Bit of a harder one, they reckon. Question 5. Okay. Well, have a go. I'll show you the answers now. Just down below here. There's question 1 and 2. Almost all of 3. They might mark that. Let's go down to 3. 3, 4, and 5. Okay. All right. I hope you've had some success there. It's a powerful area of mathematics, and it's important that you can see the value of it and use these models. All right, well, that's all from me for now, and cheers. I'll catch you in another presentation a bit later on.